Okay, good afternoon and welcome to the last session. What I'm going to talk about is high voltage, high current DC to DC converters. And by this we're meaning utility scale, approaching a megawatt or more. The first thing is probably to follow on from, or the first thing I'm going to do is talk about why we might want to build these. And that leads on quite nicely from the work that Mike's just been presenting. And after that, we'll talk about the topologies and highlight a couple of the options that we have looked at in connection with the converters theme work. That's not to say that they are the best options, the only options, but they give an indication of the type of approaches that we were thinking of investigating. No. Excellent. So why? The last two presentations, DC power can reduce losses and allow better utilization of conductor ratings. So that's proven in transmission systems. It's proven in arguably DC distribution systems on marine platforms such as ships. It also probably starts to become justified in power distribution systems or power collection systems such as, for instance, offshore wind energy, where the area of the cable network is starting to reach hundreds of kilometers. It's not got exactly the same issues as long-distance transmission, but there's still a lot of reactive power that has to be put into that cable network to keep them energized. The other driver is power electronics must accommodate growing levels of power electronic connected generation and loads. So most of the power electronic systems operate from a DC bus themselves. So why ship AC around the network purely to convert it back to DC to drive some more power electronics? So the elimination of the intermediate AC interconnection appears to be attractive. It appears that we could reduce some of the conversion stages. It's worthwhile looking through some of the drivers. This was some nice graphs which show the difference between the losses that you would see in a cable network and using a DC system at medium voltage or an AC system at medium voltage. You might argue with the ratings that they've used for the cables looking at the levels of losses, but the trend is illustrative very nicely of what's going to go on if you move from AC to DC for distribution level voltages. You can pull down the losses quite considerably. So there's an attraction to move to DC, not just at the very long distance transmission level, but potentially at medium voltage levels as well. There's also the idea that you may be able to reduce the number of conversion stages. And this is already applied. It's implied in aerospace, it's implied in marine level. So what we'll be talking here is we're talking, say, some kind of energy source, variable frequency or controlled frequency AC converted to a local DC bus. DC converts then to a fixed frequency AC system which is used for power transfer, and then most likely the way things are going, back through some more power electronics and back to control the power flow, the AC that's fed into, say, a machine. It would be applicable to then replace that AC stage with a DC stage. And it looks attractive because we've now got rid of one converter. Great. And if we could operate a whole system, a whole power flow system from here to here at the same DC voltage, that would be true. And we've got, apart from the problem of dealing with faults, we've got a gain because we've taken out some of the power electronics and some of the losses. But we need to investigate that a little bit further as to whether that applies in this utility scale integration systems where we're talking multi-megawatt and we're talking big generations and big flows of power. And a good illustrative example is the offshore wind array. And it's one of the areas that's tended to drive this type of research. And the current approach to here is something which really replicates an onshore wind farm, a variable speed wind generator, probably a large permanent magnet machine, variable frequency, converted on a back-to-back AC drive with the transformer stepping up to probably about 33 or maybe moving to 66 kV and driving an offshore collection system. For the reasons we stated at the beginning, it might be attractive to convert that to a DC system. So we would now replace this AC to DC with a DC to DC converter. It's unlikely that the appropriate voltage for the wind turbine DC bus would be the same as that which we would have to have in our collection network. So we might be, for a high voltage machine, 3 kV, maybe a bit higher for the machine bus voltage, and we'd want to probably step up to maybe 50 kilovolts. I'm not saying that's precisely, but that's the kind of area that we need to be getting that step-up ratio. Having moved from your collection network, you've probably got a second stage of conversion required to step up from 50 kilovolts up to 100 kilovolts. So this DC to DC converter, in our black box, it just looks like another power conversion stage. But implementing that and what we can achieve depends really what is going to tell us whether this type of approach to large-scale energy collection or energy distribution at the other end is going to be viable. So we need to have a DC to DC converter. Different voltages may be preferable at generation and collection and distribution levels. They're going to be DC to DC converter is going to be required to step up or step down between these stages. And if we are talking about the kind of multi-terminal networks that some people, such as Friends of the Supergrid, are mooting, these are going to be built over probably numerous numbers of years. In that time, technology is going to shift. 320, plus or minus 320 kV is established now, but there's talk of moving that up to plus or minus 400 kV in the near future. It could well move higher than that. If we want to network those systems, we're going to need DC to DC converters to be able to translate between those voltage levels. Exactly the same as they have in the AC power networks, which have been built over many years and require transformers to connect between different parts of that. There may also be a need for DC to DC converters to provide auxiliary functions. Principal drivers for that would be balancing power flows in mesh systems, allowing you to optimally share the use of the conductors, or controlling DC faults. Once you've got a DC to DC converter in the circuit, it automatically provides you that circuit breaker function. Whether it be justified in putting one there purely for that purpose is another matter. So a little bit of back to basics. We've got a number of different primary options as to how you could implement your DC to DC converter. There's the basic type of converter, which is a single switch device. It's a pulse width modulated circuit with a DC offset. And you fill that, and you pass that through a filter and extract the DC component. The other approach employs a two-stage system with an intermediate AC stage. So you've got no DC offset, and it's not a system where you filter it out. You have an intermediate AC component, and that is then rectified and put back into DC. So there's this two-stage conversion stage. That could be a passive network, it could be resonant, or it could be transformer coupled. We've got some particular challenges for this type of application which aren't there for, say, aerospace. They aren't there, say, for marine. The first one, which is the biggie, it's exactly the same problem that the issues that Mike and Carl will have to address in HVDC. We can't get a single power semiconductor device to switch these voltages. So we need to have series connection, which can be shown to work, or we need to use some kind of multi-lever or modular techniques to share the voltage between the devices. Efficiency. We primarily want to use these devices to increase the overall system efficiency. It's not something like a machine drive where we're buying the ability to control speed at the expense of the cost and the losses of the power electronics. Here, all we are trying to do is to improve energy capture. So efficiency, the aggregated cost of the losses in those converters are critical to whether they're viable. Size. Size is important. Size is particularly important if we're thinking about this in the offshore case because it's got to go on a platform. The platform's hideously expensive and probably one of the biggest obstacles to going offshore. If we want to raise switching frequencies, we want to raise the switching frequency or raise the power frequency in order to achieve the reductions in the passives, reductions in transformer size that would give us some gains in the platform size over what we could achieve with an AC connection with a 50 hertz transformer. And we want to make sure that we could get that kind of switching frequency, or to push up more precisely the power frequency, we need to make sure that we maintain the switching speeds of the individual devices, and that is in general compromised if we go for a direct series connection approach. Because you can series connect, but there's going to be some penalty paid by making sure that none of those devices hog voltage. You could look at soft switch circuits. Last one's isolation, and arguably you need to have galvanic isolation between the different power levels, the different voltage levels that you have within the system. There's a lot of options, so in terms of the studies we did, we restricted ourselves a bit. You can argue about the justification of it, but it was a means of restricting the number of topologies that we could start looking at. So we were looking to use some form of transformer, and that's really to match the type of isolation performance that exists within current AC systems. We want to get this is one we had a big argument about. They want to operate less than a kilohertz. I'll disagree with that. If you can push it up above 1 kilohertz, the gains are quite significant, but it's challenging. We wanted to avoid resonance. Again, it's arguable. We wanted to avoid resonance because we're already dealing with big volts and big amps. We don't want to increase that by oscillating voltages and oscillating currents. Again, you could argue that resonance might be beneficial because you're going to knock down the switching losses. Modularity, we want to have DC fault blocking, and we'd like to have bidirectional, if possible. So our first option is we build a pretty conventional converter using series connection. Dynamic voltage sharing is going to limit the achievable switching speeds of the individual devices. You need voltage sharing because you're taking tens, possibly hundreds of devices and trying to switch them all at the same time. It is possible to achieve it. The first generation HVDC went up to several hundred kilovolts using series switch devices. If we took that as extended that kind of approach, those type of converters achieve switching frequencies of about 1 to 2 kilohertz. So in theory, you might be able to obtain a power frequency using a square wave fundamental that pushed it up to that kind of level. But it has to be, sorry, my apologies for the typo there. If we do that, we're going to start to push up the level of losses in the converters that we've got. It's going to become pretty similar to that of an HVDC converter. The last one, which ties together with this and the dynamic voltage sharing, is we want to switch fast. If we don't switch fast, we get big losses in these devices. If we're taking a step of 400 kV and we want to switch that at a few microseconds, we're talking an enormous dV by dt applied to anything which comes downstream of that. So pretty simply, how you might do this, you could take the idea that you were going to build up something that was a transformer-coupled, series-connected inverter on either side. It could operate as a square-wave switching dual-active bridge, taking the technology from the low-voltage sector, or potentially you could pulse-width modulate these using high-voltage DC technology, filter it, and apply it to a 50 hertz transformer. At voltages up to maybe 200 kilovolts, you could certainly build it. Whether you'd want to build it or not would depend on how much someone really desired it and how much they were going to pay you. Problems. Principal problem here, the losses. I know on the previous diagrams we showed the block, the DC to AC converter as part of the conventional AC collection network, and we replaced that with a block which is a DC to DC converter. It's actually got twice the number of devices and therefore potentially twice the losses than you would have had with a conventional DC to AC conversion stage. It's going to experience very high problems with high dV by dt, potentially limited switching frequency. Our other approach is to go down the multi-level converter route. So if you can build a DC to AC converter, you've got the basic building block of a DC to DC converter. So why not use multi-level techniques? So you could apply really all of the basic structures to use in multi-level as a means of dividing the voltage stress across the devices and then synthesizing appropriate voltage to feed to a transformer to step up the voltage or step down the voltage. And they've proven themselves very effective at driving down the losses in systems which have got a power frequency of 50 to 60 hertz. Why don't we apply that? Why doesn't that directly transfer to a DC to DC converter? And the thing is that you have to switch the devices at close to the fundamental or slightly above the fundamental power frequency. So great big gains if we basically want to generate power frequencies at 50 to 60 hertz. Not so much gains if we wish to push up the switching frequency in order to minimize the size of these enormous irritating transformers that form part of the transmission system. So the advantages aren't clear. We can raise the power frequency, and if we talk about medium frequency, maybe up to 400 hertz, you certainly could just translate an MMC type topology to that. Indeed, there'd be some advantages because one of the problems with the MMC converter is the size of those capacitors. You saw the diagrams in the last presentation. They're a big part of the converter. If you push the fundamental power frequency up 50 hertz up to 400 hertz, you can reduce the size of that capacitor because those capacitors are made that big because they have got to deal with the fundamental 50 hertz power frequency energy flows, and they must smooth that energy pulsation. Push it up to 400 hertz, the size of the capacitor comes down. So that's the basic structure. We could use it. We've done some research where we played around with the type of AC waveform that you generate from the MMC converter. And it needn't be sine wave. You can play around with using trapezoidal type waveforms in order to try to minimize basically the energy transferred into these capacitors. From there we thought, is there any means of adapting that or getting some advantages? And what we did was we started looking, if we wanted to push the switching frequency up, why not use the converter so that it was operating most of the time just in the positive and negative rail, and using these cells as a means of controlling the voltage step. If we did that, we reckoned we could get away with a very small capacitance, a small arm inductance, and I'll explain why the arm inductance decreases in size later. The device voltage is still limited by the cell capacitance. In effect, what you've got now is a controlled snubber. So it's a snub. It's that capacitance acts as a clamp when you when you switch that device. So that device, the main power device, can switch as hard as it likes, as though it was a device in a single inverter. The voltage is then clamped to the capacitor, which just has to be enough to support the voltage during the transition, or stop the voltage changing during the transition. You've also got the ability to control the dV by dt. Because we can switch these in a series of steps over 5, maybe 10 microseconds, we can control the front-end dV by dt that's applied to that transformer. So you can form something that looks like a dual-active bridge, but with a soft turn-on and turn-off edge to limit the high frequency imposed upon these windings, because trying to build that type of transformer at those power levels and subject it to very high dV by dt, not only have you got the EMI, you've also got the stray or the stresses on that transformer, which is big anyway, and now it needs to be designed for high frequency. The arm currents with this design, they don't contain, unlike the MMC, they don't contain a continuous DC component to top up the capacitors. Because we're operating those cells effectively as a snubber, you only see the energy being transferred in and out during the switching transition on that slope. So we've run some, right, we've got that. So we've got the basic idea here. This is a simulation test, passive network representing the windings of the transformer. The basic voltage waveform is a square wave, but that square wave is now not controlled by trying to switch a big stack of devices all at once. It's controlled by stepping them up one by one. The voltage across the capacitance only varies at the switching instant. So each of those capacitors is only used as a clamp when you change the voltage levels. As we look here, we can see, again, simulation of the current that's drawn through the upper and lower arm. The interesting thing here is to look at this current down the bottom. And this current there, or the spikes that you can see of the current, represent what's akin to the circulating currents that are present in the MMC converter, or the classic MMC converter. And why that occurs is because when you're ramping up and down these cells, you absorb a certain amount of energy in those capacitors. It's almost as if you can treat it as a giant switch, switching very slowly, but the energy isn't absorbed in the semiconductor, it's absorbed in that capacitor. And that has to be pumped back into the supply. And one of the issues that we're looking at the moment is how much of that energy is actually pumped back into the supply and how much is dissipated elsewhere in the circuit, because we need that to work out what the actual overall system efficiency would be. So that's one approach that we took, and the advantage there is we're generating what's in effect a very big two-level converter with a clever means of controlling the dV by dt that's impressed on the transformer with something that looks like a controllable snubbing device. Not really an MMC converter, although it looks very much the same. The other approach is to try to extend the type of performance that we can get at low to medium voltage using conventional DC to DC converters and extend it up to high voltage. There's a lot of tremendously good work going on in the aerospace sector and also in marine power electronics, which is delivering high efficiency DC to DC converters at rail voltages maybe up to 2 kV. So the idea is you can take an input converter array and an output converter array and have a transformer array which connects them together. And what we're trying to do here is we're just trying to take advantage of all the advantages of all the features that we've got already. And we can input parallel connection reduces the switching device current stress, so we can work with relatively small modules. Reduced voltage stress, each module operates at the voltage rating of a single device. Size and weight should be, arguably, similar to that of an established DC to DC converter technology. I'm not totally convinced about that, but the researchers claim it. Redundancy, or to be more precise, availability could be achieved because of the array structure. It's a modular structure, and as you'll see, the disadvantage is to make this, you need to have multiple transformers, isolation, and fairly complex control. So actually, I'll skip forward to this one because no. So our building block would be something like a dual active bridge if you wanted bidirectional control. It doesn't need to be a dual active bridge or single phase dual active bridge. It could be 3-phase, or it could have a current source here with diode rectifiers. But it's just really a translation of any DC to DC converter building block. It could be resonant as well. That's then built up into some form of array. There's the standard approach, which has been around for a long time, except at much lower voltage levels. Though I think I've seen it proposed by both Alstom and Converter team. As I've seen a very old paper from Alstom France proposing something like this, and I've certainly saw something at AC/DC from Converter team. That's not going to wash if we want the voltage rail on this side to be higher than maybe 2 kilovolts, maybe 3 kilovolts. So we need to extend it up, not to just having parallel input to series output, but we need to have both parallel and series connection on the input. So each of these blocks, and there could be many more than 2 of those blocks, have to share voltage, and then each of these individual cells on this side here have to share voltage. So the control in that one approach is made quite considerably more complicated. Right. One of the disadvantages is the control that needs to be implemented. In theory, you could just operate on a common duty cycle for all converters. The disadvantage of that is that nothing ever quite matches. If you don't take into account potential mismatch between the different modules, then you're going to end up with unbalance of voltage and possibly poor dynamics. So control schemes which regulate the output voltage and then regulate the individual cell voltage with, again, current control loops to make sure that that voltage is itself regulated start to become necessary. And that results in fairly large scale requirement for transducers and feedback and relatively complicated control, as you've got a output voltage control to control the total output, and then the approach adopted here was to have a master controller and then to add offsets to the current control loops of each individual device in order to drive them back to the same DC voltage. And the types of improvement in performance, so this was one test done at simulation with misbalancing of the capacitors. This is looking at common duty cycle control, and this with a step change in input, and this is looking with the 3-term control. It's an exaggerated case insofar as the variation in capacitance is much bigger than you would normally anticipate, but the fundamental benefit of controlling each cell individually with that more complicated, more transducer heavy approach is seen here. Right, let's skip on. Now, fault ride-through. If you take this type of approach, then you've got the ability to ride through a number of fault conditions, and in order to do that, you need to have some form of. I've got the transitions messed up there. Sorry. An approach which can detect the presence of a fault, but also in this case, because it's operating with a master controller, it must be able to rotate the master in the event that that master fails. So we're looking to here with a control system which can detect, which is monitoring for any devices which are out of tolerance, taken as a 10% variation, and then switches, detects if the master is wrong and reallocates the master, and then rebalances all the voltages across the cells. The idea, going back, is that you've added redundancy. So under normal operating conditions, these capacitors are operating at a balanced voltage which is less than what could be withstood by the device ratings. In the event of a fault, we can take out one device and all these devices here increase to compensate for the loss of the voltage here. Provided you've got enough cells across there, the number of additional devices that you need to have in order to implement that redundancy should be relatively small. Very similar idea to that taken up with the MMC circuits. So we're looking at levels of mismatch here. We then fire a fault on the master converter, and we see here a dip in the output voltage. We see the output module voltage is taken down to 0 here, and the other ones step up to take over. Module inductor current, so that you've got to balance for the new voltage, the control loops activate to increase the current in each of those output inductors to drive up the output current and drive up the output voltage. So we've got an approach here which potentially could extend the operation of well-established, nice, high-efficient DC-to-DC converters. The downside is if you're going to build something like that for more than several tens of kilovolts, the number of transformers, the isolation, the number of feedback signals is going to become really quite horribly complicated. So conclusions, and I struggled to find any kind of really good conclusion. And to summarize it, you could build a high-capacity, megawatt-scale DC-to-DC converter. There's no breakthrough technology in the way the Marquette version of the MMC converter really made HV, DC to AC converters much more practical. And the reason there isn't is because you need to raise the fundamental switching frequency, or fundamental power frequency, if you're really going to make any gains out of these devices. And you also need to somehow manage to drive the efficiency of these devices up, and that means not just pushing up the switching speed, it means pushing up the conduction, pushing down the conduction losses in these devices. So you could build it, there's options there. Nothing really looks particularly nice at the moment, in my opinion. And that's me, I think, just slightly over time.